Hello students, welcome back. We define kernel and image. Kernel is set of all vectors in vector space V, the original vector space, the domain space that is being sent to the zero vector. An image is set of all image vectors that came from the domain. So it's a range basically. And then we proved kernel and image are subspaces. We went through an interesting example here, a computational example. R3, three-dimensional space, to R2, two-dimensional space, and associated with this matrix. So E1 is going to this column vector, E2 is going to this column vector, and E3 is going to that column vector. That's a matrix expression. And then the general image L of x, y, z can be obtained by matrix multiplication. And if you do the matrix multiplication, well, this is what we get. It's just matrix multiplication. Now you're looking for a kernel, so you want the L of x, y, z to be the zero vector. So what did you get? We ended up with a system of linear equations with 3 unknowns and 2 equations. Okay, all right, let's solve it. It's not too bad. Substitution works. X is equal to z, and then plug those in and do everything, and then y equals negative 2/3. X is arbitrary, so we ended up with x negative 2/3 of x, so get x out. Then x arbitrary constant, so this is scalar times 1 comma negative 2/3 comma 1. So this is a direction vector, and then x is arbitrary, so we have a line going through that direction. Here's the visualization. This xyz is xyz coordinate, gray arrows, and then the red line here, that's the kernel. The next example here, P of xyz is xy comma 0. And a projection map, and this is really easy. I mean, this is the image, xyz in general, and we're looking for a special case. The image is a zero vector. So what conclusion can I draw? That's the conclusion I can draw. Let's put up a space in between. X is 0 and y is 0, and z is arbitrary. Z, whatever it is, was killed by this projection map, so it doesn't matter. So z is arbitrary. Whenever I have x and y as 0 and z is arbitrary, then we have that's a kernel. So it's gonna be a line too, but this line is going to be a lot easier to visualize than the previous line. What kind of line is it? Well, I'll leave you there. It's easy. Hint is, it's really easy. How about the next example here? Let V be a vector space of infinitely differentiable real functions. Oh my, so there's no matrix expression, so it's going to be a hard one. Determine the kernel of the linear map L from V to V, where, oh, this is going to be a differential equation. So L of f is equals to this is equal to zero vector. What do you mean by that? So you see, so each vector here is a function. So let's consider of x. and that's equivalent to 3f double prime of x minus 2f prime of x plus 5f of x, and that's equal to 0 for all x. That's basically what you're looking for. So what is this? This is a differential equation. We are looking for a function that satisfies this condition. And how do you solve this differential equation? It's a long story. And was I crazy enough to include all that? I guess I was. Oh yes, I did. So the student who already took differential equations will be able to recognize this. If you haven't taken differential equations, then use this problem as an inspiration. The linear algebra is being used in differential equations. So that adds to the importance of this course. Let me stop here as far as this problem is concerned. Okay. How much time do I have left? Do I have enough time to complete the next two theorems, which cannot be separated? Let me try. These two theorems, 1.4 and 1.4, go in tandem. They complement each other, and they're both important. Two important theorems on images, basically. And by the way, if you go over to 1.6 and 1.7, they're both about kernels. So 1.6 and 1.7 go together about kernels, and 1.4 and 1.5 go together. They're about images. Let's talk about those images first, and let's analyze these problems. Let V and W be vector spaces, and let F from V to W be a linear map. Okay, so far so good. And V1 through Vn generate V. Then the image vectors f of v1 through f of vn generate the image space. So if v1 through vn generate, then the image vectors generate the image space. That's what this theorem is talking about. How about 1.5? 1.5 is about linear independence. So compared with generators, it's complementing the other way. Please recall the basis means generating and then linear independence put together. So we are talking about two different aspects here. Related? Kind of. Okay. Similar circumstance, this is backward. F of v1, f of v2, all the way over to f of vr. The image vectors form a linearly independent subset of image space. Then the original vectors, v1, v2 through vr, form a linearly independent subset of v. So it's backward. So here, the condition is about image vectors. Image vectors are linearly independent. Then original vectors are linearly independent. Here in previous theorem here, original vectors generate, then image vectors generate image space. Okay, let's go ahead and consider the proof. Okay, all right. Before considering the proof, let's consider the second statement. As a result, dimension of image is less than or equal to dimension of V. Let's consider the second statement first. This theorem is about generating V, but if we select not just generated but basis, no, V1, V2 through from the basis of V, then what do you get? And then the images generate So let's see. Dimension of image is gonna be, this is generating, and then the number of basis vectors versus number of generators. Number of basis vectors is going to be less than or equal because they generate, but they may not be linearly independent. In that case, we may have to throw some vectors away until we go down to linear independence. If it is already linearly independent, in that case, no problem there. If it is not, then we may have to throw some away. In short, this is what we get. Dimension of the image space is the minimal number of generators. So it's less than or equal to the number of generators, which is n here, you see, v1, v2, all the way up to vn, this particular generators, and then that is actual dimension of v, because we selected basis. So if we start with a basis, then n is dimension, and these are generators, so less than or equal to n. So that's the idea from the second statement. If form a basis not really strong, if we select okay, we are free to select any generators because the condition is generating. So we select generators that happen to be linearly independent as well, so they form basis. Then we can use this first claim, and then f1 to fn generate. So n is number of generators in this particular case, and dimension is the minimal number of generators, so less than or equal to n, so it works out. Okay, how about the first statement? Okay, what do we have to prove? We want to prove that these generate. So this is what we want to prove. Arbitrary element of image if I select any element from the image, then it can be written as a linear combination of these guys. This is basically what we want to prove. By the way, this part, let's go back to the definition of the image set. What is the image? It's a set of all the image vectors. So arbitrary element from the image looks like this, f of v for certain v. So select arbitrary image vector, and that is a linear combination of these guys. That's something we want to prove. And then what we know, well, we know v1 through vn generate v, so this is what we know. So v belongs to v, if we select the arbitrary element of capital V, then this can be written as a linear combination of v1 through vn. That we know. So this corresponds to the condition part. v1 through vn generate v. That means arbitrary element of capital V selected, then it can be written as a linear combination of v1 through vn. That's what this is. So what we need to do is to prove this using that. Let's repeat. Prove this for arbitrary element of image f. Can that be written as a linear combination of these? Basically this statement. And then this is what we have to use. Okay, let's prove it. Oh, wait a minute. This statement is incomplete. Okay, if this had been an in-class session, then somebody must have raised hand already because I didn't complete what this one is all about. So let's repeat. Let's go back. This is what we want to prove. Select an arbitrary element from the image space. Can that arbitrary element, f of v, be written as a linear combination of these guys, f of v1, f of v2, all the way over to f of vn? That's what this is all about. All right, arbitrary element of image looks like this. This is a definition. The set of all image vectors. Any image vector selected, can that be written as a linear combination of f of v1, f of v2, all the way over to f of vn? That is the question. That's what we want to prove. Now, this one is complete. We have equality here. For arbitrary selected v, vector v from vector space capital V, it can be written as a linear combination of v1, v2, all the way over to vn. So that's what we know. v1 through vn generate capital V. And then let's prove this. So we're going to prove this. So we cannot conclude that just yet. But, oops, typo. We can make this observation. This V is equal to that as we observed before. With me here. Arbitrary V can be written as a linear combination of v1 through vn. So f of v can be written as f of x1 v1 plus ... all the way over to xn vn. We just use this blue. Now we can use the property of the linear map. Oops. Oh, what am I doing? I can just copy and paste this part. And is this true? From here to there, is this true? Yes, indeed, because F is a linear map, so it preserves the linear combination. And is that what we wanted to prove all along? That's what we wanted to prove, and we indeed got it. What did he use for? We used this as an intermediate step in color-coded part. We must prove this. We know this. Therefore, we conclude that. So that completes the proof. Okay, I wanted to complete the theorem 1.5 as well, but looks like I'm out of time. So I'll stop here, and then let's have a bit of a review on 1.4 before moving on to 1.5 in the next video. Let's stop.